Swayam Prabha. Digital India. Educated India.
Welcome back to the second lecture of this module, boundary layer analysis. So, last class we finished the lecture by saying what happens if the plate is displaced at a section A by an amount delta dash. So, we displace this plate to here, for example. So, to answer that, we see that the flow rate across each section will be the same, okay, because the area is the same, but in this section BB, due to the deficit u minus u, the momentum flux across the section BB is also less than that across the section AA. True, because the velocity is different, it is a deficit of u minus u, and therefore, the momentum thickness theta is defined in terms of the momentum flux. So, we saw the boundary layer thickness, we saw the displacement thickness, right, the phenomenon, and we saw what a momentum thickness is. Now, what we are going to do is we are going to derive the displacement thickness. Okay. First, the definition: displacement thickness is the distance by which a streamline just outside the boundary layer is displaced away from the wall due to viscous effects on the plate, as we have seen in the last slide, an answer to the question which we started the lecture with. So, displacement thickness is the distance by which a streamline which is just outside the boundary layer is displaced away from the wall due to the viscous effects on the plate. Okay. This is the boundary layer. Okay. Again, look at the definition: distance by which a streamline just outside the boundary layer is displaced away from the wall due to the viscous effects on the plate. What exactly is that thickness? Delta dash x. Okay. This is the outer flow streamline, and this is the boundary layer. Okay, and the velocity v was coming here. Outside the boundary layer, as you can see, the velocity is exactly u as a function of x is v. All right. Now, we consider the flow over a smooth flat plate like this. So, there is a flow which is coming with the speed u, there is a flat plate, and at any distance x there is a section 1 1. I will remove this, okay, but just to mark, this is a section 1 1, and that is located at a distance x from the leading edge. So, this is the leading edge. The orientation is clear to you, I hope. Now, at section 1 1, we consider an elemental strip of thickness dy. Now, this dy, so this is the elemental thickness dy, and it is located at a distance y from the plate. Y again, so this is the elemental strip of thickness dy. Suppose if B is the width of the plate, okay, that is the width, then the area of the strip can be given by B into dy. The strip will have the height dy and the width is B, therefore, the area is simply B dy here. Now, the mass flux through the elemental strip is given by rho u into dA, correct. Rho u is the sort of a momentum, right, rho into u, mass into velocity. Of course, we have not considered the volume right now, but we multiply it with dA to have the mass flux. So, dA, if you put dy, this becomes rho u B into dy. Whereas, for the uniform velocity profile, so the uniform velocity profile that exists in a region below this, the mass flux is given by rho into capital U, because this is the full velocity u. Here it is u as a function of distance y, this one. Okay. So, here is rho capital U B into dy. If there was the flow was uniform, okay, and there was no plate, for example, and if you would have considered the same elemental area of thickness dy. Therefore, the reduction in the mass flux through the elemental strip compared to the uniform velocity profile will be the difference of the mass fluxes, right. This is due to uniform that is in the boundary layer, okay. Or if we take rho outside, B and dy outside, it becomes rho into u minus u into B dy. Now, the total reduction in mass flux through BC will be, we have considered in thickness of dy. So, what we are going to do? We are going to simply integrate over this length, and let us say this is, so okay, let me, so this distance is delta, okay. So, the integration goes from 0 to delta and rho u minus u B dy, that is the total reduction in mass flux through BC. I hope this is clear. This is equation number 1. Now, when the plate is displaced by delta dash such that the velocity at delta dash is equal to u, then the reduction in mass flux through the distance delta dash is going to be very simple. It is going to be rho u, because the velocity there is capital U, delta dash into B, correct. So, we have assumed that the plate is displaced by delta dash such that the velocity at delta dash is equal to the uniform velocity u that was outside the boundary layer. Then the reduction in the mass flux through that distance is going to be rho u delta dash B, because at the plate it was 0, and this should be equal to the reduction in the mass flux through the boundary layer thickness, for example, at that particular point at a distance x. So, rho u delta dash B is equal to integral 0 to delta rho u minus capital U minus small u B dy. Thus, for an incompressible fluid we obtain delta dash is equal to, what we do is we take these terms, so we take rho u and b down here, right, as the denominator, and we simply write delta dash is equal to integral 0 to delta 1 minus small u by capital U into dy, and this is the equation for the displacement thickness. So, in the numericals when you get, you are going to use this, this equation for finding the displacement thickness delta dash. Now, proceeding, what is the momentum thickness theta? So, momentum thickness theta is the loss of momentum flux in the boundary layer as compared to that of the potential flow. So, there is some loss in the momentum flux, and why that is lost? Because the presence of the viscosity due to the presence of the plate in a viscous fluid flow. Okay. Therefore, this is the loss of the momentum flux. Now, the deficit in the momentum flux for the boundary layer flow is written as the same fundamental. Now, instead of mass flux we have written momentum flux. Therefore, instead of simply rho b u minus u, there is a multiplication term of a small u as well here. So, this is the loss in the deficit in the momentum flux, okay, given by equation number 3. Now, the equation number 3 must be equal to the momentum flux in the layer of uniform speed u and thickness theta, correct? That is how we derive the displacement thickness as well. So, we equate rho b u square theta, because this is the momentum flux layer of uniform speed u and thickness theta. Okay. Or if we take this down here as a denominator, rho b will get cancelled, this will become u by u into 1 minus small u by u dy. So, this is the momentum thickness. All right. Now, there is something called energy thickness delta double dash. We are not going to derive it, but some authors define another thickness of the boundary layer based on the reduction of the kinetic energy of the fluid flow due to the velocity defect. So, the momentum thickness was due to the loss of the momentum flux, displacement was due to the loss of the mass flux, and due to the energy thickness due to reduction of the kinetic energy of the fluid due to the velocity deficit. Okay, and we will just write down the equation here. It is given as integral of 0 to delta small u by capital U into 1 minus u square by capital U square, this is the free stream velocity, into dy. Okay, now we have to make note of some important point, that is the boundary layer theory is based on the fact that the boundary layer is thin. Okay. So, at any location x, this x must be very much greater than delta boundary layer thickness and also the displacement thickness. This x must also be greater than momentum thickness and also the energy thickness. Okay. These four things means that the boundary layer is thin. boundary layer thickness delta is a function of x. Okay. This has to be assumed. These are the 1, 2 and 3. So, we are going to solve some problems that will demonstrate this momentum thickness, displacement thickness and energy thickness. Okay. See, the question is, find the displacement thickness, the momentum thickness and the energy thickness for the velocity distribution in the boundary layer, which is given by small u by capital U is equal to y by delta. Okay. This is the velocity profile. Okay. So, this is one of the most simplest problems that we are going to see in this part. So, how to solve that? What I am going to do is, I will go to my usual white screen. Okay. So, we will start writing the things that are given. So, the things that are given is small u by capital U is equal to y by delta. Okay. By definition, displacement thickness delta dash is given as to delta 1 minus u by capital U into dy. Okay. So, using this term here, we can write delta dash again as integral 0 to delta 1 minus, so this is bracket 1 minus y by delta dy. Okay. Delta dash can be written as, after integration, 0 say delta minus 1 by delta, because this is integration with respect to y, this will become y square by 2 0 to delta. Draw a line here. Okay. So, delta dash is going to be delta minus 1 by delta into delta square by 2 is equal to delta by 2. Sorry. And this delta here is boundary thickness. This is, as we told, this is displacement thickness. Okay. So, now going to momentum thickness. This is very simple. So, we have written displacement thickness in terms of boundary layer thickness. So, what I am going to do, I will erase all ink on the slides. Okay. Momentum thickness theta. So, theta definition is equal to 0 to delta u by capital U into 1 minus u by capital U dy, and this is going to be 1 to delta, this is going to be u by capital U minus u square by capital U square into dy, and using the velocity profile we can write integral 0 to delta u by capital U is going to be y by delta minus y square by delta square into dy, or removing the integration sign 1 by delta would come out, and this is going to be y square by 2. So, this is y square, and the limits is going to be 0 to delta minus this delta square is constant. So, it is coming out, and this becomes y cube by 3, and the limit is 0 to delta, right. So, momentum thickness theta can be written as delta by 2 minus delta by 3 here is equal to delta by 6, which implies delta by 6. So, this is momentum thickness okay. Now, the energy thickness, okay. Delta double dash, the definition is integral 0 to delta u by capital U into 1 minus small u square by capital U square into dy, and this is going to be 0 to delta u by small u by capital U, right, minus small u cube by capital U cube into dy, and after substituting the velocity profile, this is going to be 0 to delta, the limits y by delta minus y cube by delta cube, and all to dy. Okay, so, we have not yet integrated it. Now, the next step is to integrate, and after integrating this, what we get is 1 by delta is common. So, it comes y square by 2 0 to delta minus this comes out to be, this is constant. So, this comes out, and y cube becomes y to the power 4 by 4, and the limit is 0 to delta. Okay. And therefore, the energy thickness here is, this will come out to be delta by 2, and this comes out to be delta by 4. So, the energy thickness is coming out to be delta by 4. Energy thickness, okay, and this is boundary layer thickness. So, this is one of the simplest problems in the boundary layer analysis. So, you have to attack all the problems like this. All right. So, we proceed to the next problem. So, our next problem is find the displacement thickness, the momentum thickness and the energy thickness for the velocity distribution in the boundary layer that is given by u by capital U is equal to. So, we have another velocity profile similar to problem number 1. Okay. So, we will solve this problem as well. Okay. So, for doing that we are going to have white screen again, and as always we start with the thing that is given. What is given to us? Small u by capital U is equal to 2y by delta minus y square by delta square. Okay. And according to definition of the displacement thickness, that is delta star, definition is 0 to delta 1 minus small u by capital U into dy. So, it is quite simple. We use this velocity profile here, we plug it in and we first write integral 0 to delta is equal to 1 minus 2y by delta plus, this minus becomes plus, y square by delta square into dy. So, now there are 3 terms to integrate. All right. So, we are going to do delta dash is equal to this 1 into dy will be y 0 to delta minus 2 by delta y square by 2 0 to delta plus 1 by delta square is constant. So, and this becomes y cube by 3 0 to delta. So, displacement thickness is going to be delta minus delta plus delta by 3 and this gives us delta by 3. So, the displacement thickness is coming out to be delta by 3. Now, similarly, we have to find the momentum thickness. All right. So, theta is the momentum thickness going by the definition 0 to delta u by capital U into 1 minus small u by capital U dy. Okay. And we substitute the velocity profile here. All right. So, it will u by u minus u square by capital U square. So, it will become 2y by delta minus y square by delta square minus 4y square by delta square minus y to the power 4 divided by delta to the power 4 plus 4y cube by delta cube the whole dy, right. And now we can integrate. This will be 2 by delta y square by 2 from 0 to delta minus 1 by delta square, and this y square will turn out to be y cube by 3 0 to delta minus 4 by delta square y cube by 3, and this will be minus 1 to the power 4 delta 4, and this will become y to the power 5 by 5 from 0 to delta, and the last term is going to be 4 by delta cube outside, and y cube becomes y to the power 4 by 4, 0 to delta, and this will come out to be, the first term is going to be delta, second term is going to be minus delta by 3 minus 4 delta by 3 minus delta by 5 plus delta. So, momentum thickness is going to be 2 delta by 15. So, this is the momentum thickness. All right. Now, the the last part before we conclude today's is the energy thickness. Delta double dash. So, delta double dash, first what we do is we write the equation 0 to delta, right, u by capital U 1 minus u square by capital U square dy, right, and after we substitute the velocity profile, what we get, integral 0 to delta, it's going to be, so yeah, 2y by delta minus 8 y cube by delta cube minus 2y to the power 5 by delta to the power 5 plus 8, bear with me because so many terms, but this is the beginning, so I am not skipping anything, not trying to take anything for granted, plus 4 y to the power 4 by delta to the power 4 plus y to the power 6 by delta to the power 6 minus 4 y to the power 5 by delta to the power 5 dy. And now on integrating actually and putting in the limits, what you are going to get is delta minus delta by 3 minus 2 delta plus 12 delta by 5 minus delta plus delta by 7. So, the energy thickness is going to be 22 delta by 105. This is the energy thickness for this particular problem. So, this problem is also solved. So, now we will close this lecture and start our new lecture number 3 with by solving this problem number 3, and then we proceed to the next topic. So, that is enough for today, and I will see you in the next lecture. Thank you so much.